Okay, thanks for staying as well. It's the graveyard shift here. So my name's Jim, and I'm in Stockholm. I'm based in Stockholm at the University KTH, and I also work at a research lab. I'm going to talk about Spark, TensorFlow, distributed deep learning training in particular, and I'll talk also about our platform called HOPS. But just to kick off, because I'm an academic, I have just a little bit of background. So when the history of gravity was written many years ago, one event stuck out, and that was when a young Edmund Halley, he visited Isaac Newton, and he asked Newton a question. He said, what kind of curve will a planet describe in its orbit around the sun if we assume there's an inverse square law of attraction? And at the time, a lot of people in London particularly assumed that this was the force of gravity. It was an inverse square law of attraction. Of course, Newton knew the answer because he'd solved the problem, and from there came Principia Mathematica and gravity. So if you think about AI, and a lot has happened in the last few years, what events will be written when we write down the history of AI? One event that I don't think will be there, but it's the event that everyone is talking about this year, is how do we scale out deep learning? So Facebook released a paper in June, and they basically showed what many people suspected, that they're training their neural networks in 1 hour while we wait 2 weeks to do it. So in their paper, they showed some techniques. So they showed a very large batch size, and also using a very high learning rate that you gradually approach. They could reduce the training time from 2 weeks to 1 hour on 256 GPUs. And if you look at the chart, it says 352 there, but they only claim 256 in the paper. So that's kind of interesting, but how does it affect us as enterprises and individuals trying to work with AI? How do we get up to where Facebook are? Well, if you want to get up to where they are, you have to actually climb a hierarchy of needs, in an AI hierarchy of needs, kind of like Maslow's hierarchy of needs. And I think Ali Ghodsi touched on some of this in his keynote. First, you need to handle large volumes of data. So you need to be able to ingest data. You need to be able to ingest it reliably. You need to be able to do analytics on your data. And then, only then, with clean data, can you start doing machine learning. And as you get higher up in the stack, you then need to do more and more prediction. So at the bottom of the stack, you're really doing analytics. But to get higher up in the stack, you need to do deep learning, machine learning, label your data, label your training data. And at the very top of the stack, it's really distributed deep learning, and that's where Facebook are today. So I'm going to talk a bit today about how we get there with Spark and TensorFlow, and also with our platform HOPS. Now, if you're an organization, that may be relevant to you, but as a researcher or as a practitioner, you'll care more about this slide. So this slide will tell you about, if you're training deep learning models, how long will it take you? So a normal researcher will probably have 1 GPU or maybe a couple of GPUs in a box, and they're going to take a couple of weeks to train ImageNet. If they have a box, if they're lucky enough to have a nice big box with 8 GPUs, they might get it down to a couple of days. What you really want to do as a machine learning researcher is you also want to run many parallel experiments. You want to do things like hyperparameter optimization, to do that on many GPU servers. And as you get higher up in the stack, you also want to do distributed deep learning to reduce your training time. At the very top, you can see that I've got 2 different versions of distributed deep learning. One is called parameter server model, and the other one is called all-reduce. So I'm going to talk a bit about those today. But before I go on to talk about them, I'm just going to tell you where we are today. So right now, if you want to get to the very top, you need to do this on-premise. And that's mostly because networking is the bottleneck. So at the very highest level, what companies like Facebook and Google and so on do is they use very low latency, high network bandwidth technology like InfiniBand and RDMA. On the public clouds, you don't have access to that today. I'm sure it will come in future. But you can get up to the level of doing parallel experiments in GPU servers, and it works quite well in clouds. Okay, so if you're a researcher, this would be nice. You would, you get instant gratification by training your models quickly. And in particular, you don't want to, have this Google envy that we tend to have, that everyone says, well, Google have better tools than us, and we'd like to be like that. So our goal will be to try and get there. And then the question is, well, how do I get there? Well, you can use the P100s that Amazon announced today, or you can buy hardware if you're going to do it on-premise. So I'm going to talk a little bit about on-prem. And if you're doing it on-prem, there's kind of a Ferrari model you can see there, which is the NVIDIA box, the DGX1. And they give you 8 top-end GPUs, either P100s or V100s. But there's another box that's become very, very popular, which is a commodity box, which has 10 of the commodity cards. NVIDIA will tell you not to use them. This kind of reminds me of going back 10 years where the vendor said, do not use commodity disks in your servers. They will break. Use enterprise disks. And we know how that one finished up. So nowadays, a lot of people are buying. We bought a couple of these 15,000 euro boxes. You get 20 GPUs for that. They're quite good. They're about 60% of the performance for deep learning of the P100s for CondNets. And you can stick InfiniBand in there as well. So InfiniBand is not that expensive if you're curious about that. So if you have a box and we want to do distributed deep learning, what can we do from there? Well, actually, the first box that you might want to get is this Volkswagen, not the Ferrari. And just to give you an idea about how it looks like, it's slightly different to a typical commodity server. Because in the typical commodity server, your PCI slots will connect to the 2 CPUs at the top. So you can see that the 10 GPUs at the bottom are all connecting to a single CPU. And that's because the link between the CPUs, the QPI link, tends to be a bottleneck. So if your GPUs are talking to each other over that 8 gigabit or 9 gigabit link, that will bottleneck out when you're training. So what you try to do is you put them all into the same PCI single root complex, and that helps reduce that bottleneck. So if you buy one of those boxes, you can expect things like GANs, general adversarial networks, to scale out pretty much near perfectly. And this is from Serve the Homes. I take no responsibility for the figures shown here, but they scale out quite well. So the interesting thing is that if you're to buy 1 or 2 of these, and maybe some of the Ferraris, the DGX1s, how do we rack them up? How do we put them together to make them available as a service on which I want to run Spark and TensorFlow code? And typically what people do is they won't want to buy new racks. They won't want to buy new power units. So they'll spread them out over the cluster. So typically two of these servers per rack, you can put them in without having to do too much with your power supplies. And that way you can build up a network. And if you connect them with InfiniBand, even better. OK, so what you need to do once you've got a network of these GPU servers, you would like to then run your jobs, right? So the kind of things you might want to do with Spark and TensorFlow is say, well, I'd like to run a single GPU experiment, or I'd like to do some hyperparameter tuning, run lots of parallel experiments on lots of hosts with GPUs, or when you then are happy enough with your job and you think, okay, this looks pretty good, I'm happy with my hyperparameters, I'm happy it's going to work, now I'm going to run a large distributed training job. And that's typically the workflow that people will go through when they're developing deep neural networks. So we looked at this and we said, okay, we're going to try and support this. We have a platform for it. But the single GPU experiment really just becomes a parallel experiment of size 1. So really you only need to care about the two kind of models for allocating GPUs to applications. Either you're going to do parallel experiments or distributed training jobs. And then the type of GPU servers you might want to have, you might want to have many of the commodity ones because you want to do a lot of hyperparameter search and a lot of interactive analytics. But then when it gets to powerful training, you might decide to put some of the DGX1s in there. So it's nice to have a mix of different types of servers there to best improve your productivity. Okay, so you can use this today. We have a platform called Hops. It's a new distribution of Hadoop, and we support GPUs as a resource. So we have our own implementation of Yarn. We have Yarn we have GPUs in Yarn on Hops, and you can ask from a Jupyter application. You can say, well, I would like to have 4 GPUs on any host for parallel experiments. I'd like to have 10 GPUs on one host because you're going to do training, and you'd like to have them all co-located on the same host to reduce any potential bottlenecks over the network. You might decide to do a large distributed training experiment and say, I want 100 GPUs on 10 hosts with InfiniBand on the host. So we can use node labeling in Yarn to basically say, this node has InfiniBand, and then we can use our version of Yarn to say, give me 100 GPUs on 10 hosts. And then if you have heterogeneous GPU cards in your platform, you might want to then change your labels to say, this is an InfiniBand P100 or an InfiniBand 1080 Ti server. Okay, so what Hops is it's not just Yarn. We're most well known for as being the world's fastest Hadoop distribution. We re-implemented the name node in Hadoop in HDFS, and we made it distributed. And by doing so, on Spotify's Hadoop workload, we got 16x throughput. We can make much larger clusters. And we've recently also finished, and it's been released, support for small files. So small files are now stored in an in-memory distributed database rather than out in the cluster, and then we get huge improvements in terms of writing and reading, and also reduced latency. And the platform won this year the IEEE Scale Prize. Okay, so that's a bit about how to allocate your resources to your applications. What about actually writing TensorFlow applications within the Spark framework? Right now, there's two main approaches to it that you'll find. There's a number of different frameworks, first of all. The ones that you may have heard about here are mostly deep learning pipelines by Databricks, which built on the TensorFrames work from Tim Hunter before. That model is really espousing a tight integration where you really just write Spark applications and you try and abstract away the deep learning library, whether it's TensorFlow or whether it's MXNet or Caffe2 or whatever your library is. The other model that we're approaching, and also TensorFlow and Spark by Yahoo, they support both kind of in some way, TensorFlow and Spark by Yahoo, but they also support a looser integration model where you write TensorFlow code, so TensorFlow code in Python, and really Spark is a wrapper to handle distribution, security, and other elements around it. Okay, so let's look at some code. This is deep learning pipelines from Databricks. What you can see here mostly are data frames, and then we have a TensorFlow graph. But once you're inside the TensorFlow graph, you're really just working with data frames to do transformations and then to do some model fitting. And then what's interesting in their model is the use of Spark SQL for inferencing. So when you need to do your model serving, you can actually serve directly using Spark SQL. So that's quite from a programming perspective, that's quite nice. So the API, I would say, is quite clean. If you're used to Spark, this is a nice way to go. If you're not used to Spark and you write a lot of TensorFlow code and Spark kind of scares you, we have a very simple model for you. It's called TF Launcher on hops. And basically what it will do is it will allow you to write pure TensorFlow code inside a mapper. So the only thing you need to do is wrap that model function there and launch it from this TF Launcher command at the bottom there. So it's basically going to launch a TF job as a mapper in Spark. And you can see we can pass in hyperparameters in this dict, args dict. And then we have a bunch of libraries and utilities to help you work with TensorBoard and HDFS and GPU devices and things like that. So this particular model will launch one mapper with one GPU, but of course you can extend it to work with multiple parallel experiments. So if you have hundreds of GPUs, you can launch hundreds of parallel experiments on hundreds of GPUs. So currently we have this very simple model, the args dict, which will contain all of your hyperparameters, but of course we're going to extend this to include things like the estimators and pipelines and so on that have been talked about a lot at the conference. So this particular model, this particular code you see here will launch 3 executors with 3 hyperparameter configurations. You'll need to, if you had, for example, a grid parameter search, and if you had an evaluator and a pipeline, you could then discover what the best hyperparameters were. But in this particular simple example, you'll have to do that yourself with TensorBoard or something like that. So the other thing that you may not be aware of in TensorFlow is that they're kind of moving over to the Spark space a bit. So since 1.4, which is a release candidate right now, we have tf.data has made it from contrib into core. It's now part of core TensorFlow. And they also support estimators. There's also a transformer project there. So you can do a lot of your data input manipulation in TensorFlow itself. So you can do it inside the mappers if you want to. And you kind of might say, well, why would I do that? I can just feed in RDDs directly to feed my TensorFlow training functions. Well, you may want to do that, but the problem is that there's going to be a single Python thread deserializing your RDDs and pushing them in, and you will bottleneck on it. So right now, what people are doing is they're using input pipelines. They're using queues in TensorFlow, and if you're using the dataset API, you'll use this TF record dataset API. Okay, so distributed TensorFlow, if we move on to that, so we're moving beyond the distributed pipelines, deep learning pipelines, and our own stuff, TF Launcher. We have the parameter server model from TensorFlow and Spark in Yahoo, and also distributed TensorFlow. So TensorFlow has its own model called distributed TensorFlow. I'm not going to talk about it today. And then the state of the art right now is the all-reduce algorithm, which typically runs on top of MPI. And if you want to get good performance, you'll run it on InfiniBand networking as well. Now, there's two current implementations for TensorFlow. One is by Uber, and they had a blog post about it this week. And the other is by Baidu. So what we've done is we've actually added support for Horovod by Uber to Spark. So you can now run Horovod from within a Spark application. I'll talk about it in a minute. Before I get onto that, you may be familiar with distributed training in TensorFlow and deep learning and say, well, what are you going to do? Asynchronous stochastic gradient descent or synchronous? And a few years ago, the asynchronous model, or Hogwild as it's commonly known, was very popular, and Jeff Dean had a well-known paper on it. But a paper came out last year by Sami Benjo's group in Google, and they basically showed that synchronous stochastic gradient descent, that's gradient descent where you wait between iterations for all the workers to synchronize on the current model state and before you go to the next iteration, that converges better, and you can make it scale out. So not many people are doing asynchronous SGD. I'm just going to talk about synchronous SGD. So the TensorFlow model and TensorFlow and Spark model is synchronous SGD, and each worker will read in data independently. So each worker, these GPUs here, will be reading in its own set of samples independently. They'll calculate the gradients on the samples that they've read in using a copy of the same model. All the workers have a copy of the same model. They pass their gradients up to the parameter servers, and the parameter servers aggregates them, and on the next iteration, it will send them down and broadcast them all down to the workers. So that's the current model you find in TensorFlow, distributed TensorFlow. TensorFlow and Spark wraps this model in Spark, and it provides two modes, the RDD mode, it's called Spark mode, and then a TensorFlow mode where you read your data maybe from HDFS. And you can see some code here for it. You start a cluster, you train a cluster, you call inferencing. You do have to rewrite your TensorFlow applications a bit to work in this model. You can use Spark streaming in TensorFlow and Spark. It's not structured Spark streaming. You can use that in the Databricks deep learning pipelines model. But I'm not going to say too much more about that. So the one that's interesting from my perspective is the all-reduce model. And the all-reduce model kind of looks like this. You have each GPU or each GPU server connected in a ring, and they're all using their own local bandwidth to send and receive. They're only going to send to one neighbor and receive from another neighbor. So compared to the hierarchical model with parameter servers, every node is contributing all of their available bandwidth to calculating the new gradients. And this is kind of what it will look like when you connect hosts, because hosts won't have one GPU, they'll have many GPUs. You basically want to minimize the amount of network traffic that goes between GPU servers. And you can do it by connecting them in a ring like that. So what's interesting about this model is it's not particularly fault tolerant. It's very sensitive to slow links. So this will be as fast as the slowest link. So if you have stragglers, if you're working in a shared cloud environment, this may not perform particularly well. You just need one link or one host to be slow, and the whole thing will slow down. So you may not know what all-reduce is, so I'll give you a quick overview of it. The way it would work if you had a deep neural network with 4 layers, as we can see here, and you had 4 GPUs, is that each layer will independently do the forward pass on the samples, and then they'll start using backcrop. They'll calculate the gradients at each layer. But after they've calculated the gradients at each layer, they can send those gradients in parallel while they're doing computing. So you're overlapping network transfer of gradients with computing the next layer. And that's different to the distributed TensorFlow model that we saw earlier. So you get a lot of boost from that, and as you propagate down from the top layer down to the bottom layer, you're interleaving compute and network communication, and when you've done it, you've finished the end of an iteration, and then you go to the next iteration. So how all-reduce looks like in code, this is an example that we have from hops, is that it's much easier actually to program than the distributed TensorFlow model and also Yahoo's TensorFlow and Spark model. So you can see that the only things you need to do is actually init the Horovod or the HVD object. You then need to wrap the optimizer in the Horovod optimizer, and then you need to find out which is the chief worker and do some things there as opposed to the other worker. But otherwise, the code is pretty much pure TensorFlow code in there. So how does it perform? I guess this is what most people care about. You could have told us this earlier, and we would have had skipped all of this. Well, if you want to look at just one figure to point it out, it's the one in the bottom right-hand corner for you. You can see that for a denser model, which is VGG16, so Inception is not a very dense model, it's not very big, you don't need to broadcast that much data on each iteration. But VGG is bigger, and you do have to broadcast more data. You can see that basically distributed TensorFlow is poor. You don't get any speed up on 64 GPUs on 4 servers. So this is figures by Uber. This is not peer-reviewed, so I don't stand by it, but this is basically what they've seen and reported. And they're not a vendor, so they don't have an interest in that. But on their particular model, the all-reduced model, they're getting really good scale-up, even up to they're getting 40x scale-up on 64 nodes, which is pretty nice. That's not even on InfiniBand, that's just on 40 gigabit Ethernet. So what's the lesson to learn for there with distributed training? Well, the network is the bottleneck. You need to make sure that you reduce network communication time. And you can see that all reduce is actually optimal in terms of network bandwidth usage as an algorithm. So what do we do? So these are all pretty cool distributed training approaches. We're trying to support them in hops. Our platform, we have a UI-driven way of using hops. It's called HopsWorks. It's a stack. It has a REST API, and it has a nice UI that hopefully I'll get to show in a second. It has lots of services inside it. We've had talks at the Spark Summit before on Spark Streaming, and we support other platforms that I may be allowed to mention, like Flink and TensorFlow. And we have notebooks like Zeppelin and Jupyter as well. It's open source, and you can download it. But what makes it slightly different is that we have new abstractions. We have the notion of a project in hops. And a project is like a GitHub project, which has users and data sets in it. And a project can be any grouping of users and data sets, and each one runs as an isolated unit. It's kind of like a sandbox. You can't copy data from one to the other without permissions. You can explicitly share data sets between projects, but it becomes a nice abstraction with which users can develop safe code. So what we support in here, which is very important if you're working in Python and you're working particularly in a Hadoop environment, is that you can install different Conda libraries for every project. You can search for them, install them, and you can have your own version. And that's been a real pain in the Hadoop community in recent years. So we have a nice solution for that. We also have a service we're launching now, which is distributed data sets, so peer-to-peer sharing of large machine learning data sets, things like ImageNet and YouTube 8M. And I was going to do a quick demo. I think I have a couple of minutes, so you can basically see what's happening. But this demo is going to run near the Arctic Circle in northern Sweden. We have a data center at RISE. And on that, we have companies and researchers around Sweden using the platform. We have a couple of hundred users. And let's see if this is still running here. So this is the platform here. You can see we have our projects over here on the right-hand side. I have a demo on TensorFlow and Spark, and one on all-reduce, and one on the parallel experiments. I started this one running so we can see, this is TensorFlow and Spark. We can see if it's up right now. And basically, you can see the Spark worker running here, and inside it we have a tensor board. And in this particular one, I'm actually training Inception. So it's training the entire Inception network. We can see it is coming up here. Okay, it takes a little while to load. So we can see then we have some results of it training in our tensor board. You can kill that pretty easily. This is a Jupyter notebook. I can open it here if I have it open. This is the actual code for TensorFlow and Spark. You can see it there. Yeah, you can make it a bit bigger. And you can see here that it's basically just a TensorFlow application with this cluster. If we go down to the main part, we can see that you have to decide on your input mode, and then you have to create your number of executors, your number of parameter servers, and then your training function here. The model fitting function looks pretty straightforward. So I have a couple of other notebooks. I don't know if I'll have time to look at them. We can have a look at the code in any case. Let's see. I come back here. So we can look at all-reduce, which is the Uber one. I need to actually start the notebook server for this. Okay. So there we go. So the platform supports Zeppelin as well as a notebook server, not just Jupyter, but we find that a lot of people like to use Jupyter. It's become very popular. And the code you can see here for all reduce. It's very straightforward, very simple. It's basically this is a two-level convnet. It's MNIST. And you can see that we just have to call HVD init. And then we can wrap our optimizer inside the Horovod object. And then basically we need to do a couple of, if we want to do a bit of work as the chief worker, we do it there. Otherwise, we just call normal training step. We can collect it. So that gives you a little flavor of the platform. If you want to play with it, you can see that you can register your account at spark.hops.site, and you can run. There's actually also a tour that you can just click through to run a TensorFlow application. We'll have that up for today in any case, and we'll probably shut it down soon enough. You can install the platform today. You can go to the website, hops.io, and there's a shell script for installing it on Ubuntu machines. And there's also a way of installing it with Chef. It's fully open source. But just to conclude, what I've talked about is TensorFlow and Spark. There's a lot of different frameworks out there. You have the tight integration with deep learning pipelines, and then we have the TensorFlow and Spark and Hops approaches, which is, I guess, looser integration with Spark. And what we've done with the Hops project is we've added GPUs as a resource. So now we can launch large jobs and manage them in a single cluster. And it feels kind of nice for a Python programmer because you have support for Conda, you have Jupyter. And if you're interested in some of this, if you're interested in the commodity GPU servers and how you get this stuff up and running, you can go to our company site, Logical Clocks. And we have a beta program in process at the moment for people who want to get started. We do AI all the way up to the top. I teach a course in distributed deep learning, which is quite good, starting next week. And a lot of people worked on the project. So this is their work rather than I'm just one of very many. If you like our work, you can star us on GitHub. You can follow us on Twitter. And we are the only European Hadoop distribution. So with that, thank you.
Awesome. We have time for a couple questions. If you have any, please come up and use the microphones in the middle of the auditorium.
So the question was, how does this compare with GPU instances on AWS? Okay, so yeah, you can, I mean, I saw today you can get 8 GPU instances, 8 P100 instances, or V100 instances on a single server. I think they were $25, $40 an hour. That's fine. You can get your training time for ImageNet down to a day with that. That's fine. But what we're talking about is where are we going with distributed deep learning? And I think we're going the same way that we went with Spark and with Hadoop. We went to commodity and we went to scale out. So, you know, right now, networking is the problem on AWS. It's hard. You can't get 40 gigabit. You can't get InfiniBand. So you're going to bottleneck on that. If you try to do distributed, if you try to run Horovod or something, you'll have difficulty scaling to very high levels.
Does training in a distributed manner using either of those algorithms affect the end accuracy of the model?
Okay, so the question was, does training affect the end accuracy of the model? Would that?
By using a distributed algorithm.
Okay, yeah, by using a distributed algorithm. If you're doing synchronous stochastic gradient descent, it doesn't. If you were to use the asynchronous Hogwild model, yes, it would. Okay, so.
Awesome. If there are no more questions, then let's thank Jim Dowling for his talk.
Thanks.